So really, another really interesting thing is not only does light have a wave-particle duality, it behaves as a wave sometimes and a particle at others, matter does as well. Do you remember when we started the semester, I said there was another type of wave called matter waves. Actual physical objects can display wave properties. They have a wave nature. Now it turns out the mass of the object needs to be really, really tiny for that wave nature to be obvious, to be noticeable. But matter, just meaning stuff with mass, has a wave nature as well as a particle nature. We're used to the particle nature, talking about kinetic energy and potential energy and so forth. But it does have a wave nature as well. The wavelength of a matter wave is called the de Broglie wavelength. It's related to the momentum, the linear momentum of the object. So number one, the object has to be moving to display a wave nature. You remember momentum is mass times velocity. So it depends upon how fast the object is moving as well as how massive it is. So this h is still Planck's constant, still a really, really tiny number. Mass needs to be really, really small to get any sort of noticeable type of wavelength. For example, electrons. It's really easy to notice the wave nature of an electron. That's what electron microscopes are all about. Rather than using visible light to look at whatever you're trying to look at, they use electrons. And because the mass is so small on an electron, we get a reasonable wavelength that we can work with. Okay? Turns out, typically, the wavelength of an electron is smaller than visible light. When you're using microscopes, the size of the object in relation to the wavelength of the light you're trying to use, or the wavelength of whatever you're trying to use, you cannot see anything smaller than the wavelength of what you're using. So if you're using a visible light microscope, you cannot see anything smaller than 400 to 700 nanometers. You can certainly see anything bigger than that, but you can't see anything smaller than that. When it comes to looking at, for example, cells, so if you're into biology, you look at the cells, well, the cells are smaller than your nanometers. You can see the cell, and you can see a little clump that's the nucleus of the cell, but you can't make anything out. If you use an electron microscope with a smaller wavelength, you can actually see inside the cell, and you can see all the little individual pieces of the cell. It's pretty cool. So matter waves, protons, electrons, small atoms would all display a de Broglie wavelength that was noticeable. Whereas us, our mass is too large. The wavelength would be too incredibly tiny for any sort of wave nature to be noticeable.
And h is just constant?
H is a constant. It's Planck's constant. Okay, which brings us to the final relationship. Kind of weird. Call it electron in a box. Now, I don't know when you're going to toss an electron in a box. But if you think of it in terms of orbitals, you've had chemistry before, the SPDF orbitals, those are probability regions where you would find your electrons. You can think of those as your box if you want. A confined region where the electron needs to exist. You don't know where exactly in the region it is, but a region where you would find it. With an electron in a box, scientists assume that the motion of the electron in there is some sort of resonant motion. So there's some sort of resonance that that electron reaches in terms of how it moves. So we make it analogous to a standing wave. It has a wave nature. Resonance with waves are standing waves. It's like the wave on a string. So we say that the wavelength then must be something similar to the equation we had for the standing waves. Now, when we talked about standing waves before, we used 2L over m, where m was our integer. Your book uses n. It still means the same thing. N is just your integer, so forth. N can be 1 would be your fundamental, and 2 would be your second harmonic, and 3 would be third harmonic, and so forth. Well, if wavelength, if we have some sort of resonance, so something analogous to a standing wave, and we know that the wavelength in terms of the de Broglie wavelength is h over momentum, we can set these equal to each other. H over the momentum will equal 2L over n. What that means, if we solve for the momentum, we get hn over 2L. H being Planck's constant, n being just an integer, L being the dimensions of your box. So the dimensions of the region where the electron is allowed to move. Notice, momentum can only have specific values. H is a constant, L is going to be constant for any given orbital, n has to be an integer. So we can have h over 2L, we can have 2h over 2L, we can have 3h over 2L. Because the momentum can't be any old value you want, it has to be a specific value, we say that it's quantized. There's only specific momentum values that that particular electron would be allowed to have in that particular orbital, in that particular size of box. N is called the quantum number. It's still just the integer. It's the 1, 2, 3, 4, 5, so forth. But they call it the quantum number. So there's only very specific values of momentum that your electron can have, which means there's only a certain amount of energy, only specific amounts of energy that it can have as well. If you think about energy, back to kinetic energy was 1/2 mv squared. We can write it also as momentum squared over 2m. Well, if we plug this in, momentum square it over 2m, we get h squared, n squared, over 2 squared, but 2 squared times 2 is 8, m L squared. And again, with the energy as well, there's only going to be certain allowed energy levels, amounts of energy that your electron can have. This is what describes the energy levels inside of your orbital. This is why we get very specific wavelengths emitted by different atoms. These are different for different atoms. Mass is different. Depending upon the atom, atomically it would be different. If you were just looking at the electron, the mass would just be the mass of an electron. By the way, the mass of an electron is on the inside cover of your book. It's also on the test notes, as well as the mass of a proton. So H is just our constant, N is the quantum number, it's 1, 2, 3, 4, 5, so forth. L is the dimension of your box, which you can think of it in terms of orbitals if you'd like. And M, if you're talking about your electron, is the mass of your electron. So there's very specific energy levels that that electron can have within that atom. Energy is also quantized. There's only specific energy allowed levels. And so you end up with specific energies for different atoms, and therefore unique fingerprints if you start getting light emitted from the atom. Questions?
What do we do with that?
You can look at energy levels in an atom. So basically, if you knew the size of your orbital, you know you have an electron in there, you can find, just plugging in different n values, you can find the different allowed energy levels that that electron can exist at. And then you could find, for example, say an electron jumped from energy level 2 to energy level 1. You could, N2, find the energy, N1, find the energy. That will equal the energy that the photon is emitted when it jumps down.
Oh.
So you can find the frequency specific to that atom that can be emitted. So, interesting that way.